The last reaction we'll talk about today, and the first one we'll talk about in our next lecture, is the addition of halogens. So not HX, but HX2 molecules onto alkenes. And this reaction adds two atoms of halogen, and this can be bromine, chlorine, over the double bond. To produce this vicinal dihalide. But a question that needs to be asked here is, what is a dielectrophile? What is the E plus species that is actually reacting with the double bond? Because so far all the molecules we've seen were polarized in a way that we could clearly identify electrophile and a nucleophile. In this case, what is crucial in these reactions is the polarizability of halogens. And so bromine molecule, which reacts really well, is highly polarizable, and it's even more polarizable in the presence of electron-rich double bonds, which can attack one of the bromines, and this can eliminate the other bromine atom while simultaneously attacking back onto the carbon skeleton to give us this triangular species reminiscent of mercurinium ions plus Br minus. Okay. Now, this species is known as bromonium ion, and it's one of the many halonium ions. So this can be a chloronium or iodonium, which is a cation. It's relatively stable, but it's strained because of the three-membered ring and therefore easily open. And indeed, that is what happens immediately in the next step. When the Br minus now opens up this thing to give us the vicinal dibromide. Now this reaction is very reminiscent of an SN2 reaction. Indeed, this is an SN2 reaction of sorts, which means that it occurs with an inversion of stereochemistry. And so if we look at this substrate and have it react with bromine, the first step will be elimination of this bromide to give us the bromonium intermediate, which will again preserve the stereochemistry of the starting material, and the two phenyl groups will be on the opposite sides of the three-membered ring. And now this bromonium intermediate can be attacked from either of the two positions to give us inversion of stereochemistry in the stereocenter. Phenyl group here, hydrogen here, and it looks like this. And so this is a very much similar to the SN2 reaction. Okay? Now in this case, and to illustrate this, so what results in cyclic systems, to illustrate this on the example, is that first molecule of bromine forms this bromonium ion, which looks like this, and this bromonium ion can now be opened from the opposite side to give us two possible enantiomers. This will be one if the bromide attacks from the bottom carbon, and this will be the other if bromide attacks from the top carbon. This is roughly how stereochemically this reaction proceeds, and we will continue talking about it the next time, where this will introduce us to a whole new series of alkene reactions. To sum this up, we've seen about half of reactions that alkene undergo so far. And what is a recurrent theme in all these reactions is that alkenes are subjected to electrophilic additions, which are different from the reactions we've seen so far, such as eliminations and substitutions, which are nucleophilic substitutions. This is all fueled by the weak pi bond, which is also electron-rich, and it's the first thing to go in an alkene, which indeed drives most of its reactivity. Several reactions proceed according to the Markovnikov rule, which places hydrogen onto the least substituted of the carbons. But there are two reactions, namely hydroboration and radical assisted addition of HBr, that give us anti-McCormick product. These reactions are useful because they're complementary to the reactions that form the majority of alkene reactions, and those are the ones that proceed with McCormick addition. That's it for today, and we'll continue next time with more alkene reactions.